Okay, so we're going to talk about multispectral coherence really quickly. Multispectral coherence is where you are going to break apart your broadband data, so your full spectrum, full frequency band, into more discrete frequency bands that allow you to see more in coherence. And so just to set up the problem, I've talked about this in a few videos. Here we've got broadband data. We're looking at a time slice, and you can see a gap in the seismic. Hold on. All right, so we've got the fault. We've got the fault there. Here we've got a gap. And so if we look at the cross sections through it, we can clearly see, if we think about ourselves as an algorithm, that a algorithm would not detect much coherence, along these horizons because they're very strong on either side of the fault. But we as a human would see, the fault continuing through it. So multispectral coherence is one way we can kind of get around this problem. So, just as another example, here we've got the full bandwidth data. We can see a few gaps in the seismic. And then when we look at it at 36 hertz, we can see that that fault is much more clearly imaged. Same at 55 hertz. So you do have to spend a little bit of time looking at different frequency spectrums to figure out which frequencies will help you out, but it's well worth it for the results. A lot of times what we'll do in AASPI is we'll combine 3 different frequency spectrums using RGB, just like we would do with spectral decomposition. So we would have 3 different spectral voices, assign them to red, green, blue, and then we could create our output. So this has been really good for a lot of reasons. This is a quick example showing you the broadband data up here on the upper left-hand side of some channels with some karst collapse in the Tarim Basin of China. And then looking at the data just around certain frequencies, so different spectral voices, we've got 18 hertz, 25 hertz, and 38 hertz. And so you can notice there's different continuation of these kind of channels or caverns that you're able to pick out in different frequencies. And so that's why it's important to kind of break it down. And so here's an example looking at the peak frequency on the left-hand side and then picking out the frequencies that are really important. In this case, it's an RGB blend of 10, 30, and 60 hertz. And you can very clearly see the continuation of this channel system in the multispectral coherence. So you can also do multispectral with more than 3 components. In this case, and this is a great paper by Bin Liu that we have up on our AASPI website. In this case, he's looking at 6 different spectral voices, and you can sum them together by weighting each individual component differently. It can be adaptive the way you want it to be. And so we've got all the theory up on our website. And just to kind of end with a few more examples, since I'm trying to keep this to 5 minutes or so, here we've got the coherency using the original broadband seismic data before doing structure-oriented filtering. Now, after doing structural-oriented filtering, and you can notice some differences, and I'm going to go back and forth. So before SOF, after SOF. So of course, cleaning up your data, very important to do. You see those results in all your seismic attributes. Here we've got multispectral coherence using equally spaced voice components. Okay, so it's the way we're choosing which frequencies to use. And you can see we're kind of missing a little bit of data. If you focus on those red ovals, you could kind of see some of the differences. Here we're using multispectral coherence with exponentially spaced CWT voice components. With this channel system, you can see the green arrows are pointing out some really cool kind of features, abandoned channels down below. And then here doing multispectral coherence with those exponentially spaced maximum entropy voice components. So doing a slightly different algorithm is really bringing out some of that information. So if you're trying to understand the structure, the stratigraphic architecture of this channel, these are some techniques that you may want to use. Looking at another example, here we've got the coherence on the original broadband seismic data before SOF, just as like the comparison. So a couple key points, just to keep in mind is that multispectral coherence can really improve your edge illumination. It can bring out structural differences. It can bring out stratigraphic differences. The different ways that you choose which frequencies or which voices to use in your combination is really important too. You can do simple blending with RGB for a visual. You can also weight them differently. So a lot of things that you could spend a nice Friday afternoon playing around with in order to get more information out of your seismic data. Thanks.